company in the area. I have a pretty wide background, including embedded analog, digital power, RF, circuit board design. I call myself a novice Raspberry Pi user. I'm an experienced Arduino user. I've done about 20 years of experience doing a lot of other small processors, the embedded, custom embedded boards, like 8051s, PICs, ARMs. I've been an engineering hobbyist for 37 years. What am I doing here today? Well, I want to basically try to communicate a little bit of basic electrical engineering that's relevant to Raspberry Pi and Arduino users to help you interface the real world successfully. My targeted audience is really hardware novices and people who have more of a software background that want to delve more into Raspberry Pis to control hardware. So most of the techniques I'm going to show you today are very generic techniques that are applicable to other platforms like Arduino. I'm going to try to show techniques that you can implement with a very limited number of very basic and inexpensive parts, so you can adapt and make things. Okay, let's talk a little bit about the structure of a Raspberry Pi output pin a little bit. It helps to understand that. So there's 40 pins available on a Raspberry Pi. They're called GPIO pins, general purpose input output pins. All of those pins are based on 3.3 volt logic. That means they will not tolerate 5 volt input on them. You will blow up the Raspberry Pi and try to put 5 volt signals in. They can source or sink up to about 16 milliamps per pin, which isn't very much, depending on how the pins are configured. The Raspberry Pi 3, getting information on the Raspberry Pi 3 on what it's actually capable of is a little bit challenging. It was designed for about 3 milliamps per pin for a maximum total of 120 milliamps total for all the I/O pins. So it's really not designed to drive a lot of current or power. It's really designed just for data. So you can, one thing that's kind of interesting features, if you look at, I don't have a pointer, but you can actually configure the inputs to use hysteresis, which is kind of a nice feature that if you look at the triangle thing where it says input there with a little kind of like squiggly line thing on it, that's showing what's called a Schmidt trigger inverter or Schmidt trigger buffer. So if you have a kind of a sloppy signal and you use that, it'll square it up very nicely. That's good to reduce chatter. You can also, there's a configurable pull up and pull down that's available on each pin as well. That's the two transistors you kind of see there at the bottom part, so pull up and pull down. So if you turn that on, basically it ties that resistor that's shown there, it's about 50 kiloohms, to the input pin. So the nice thing there is if you want to have like a push button, and you want to just hook it up, you can use that pull up or pull down, so when you hit the button, it just works. You don't have to actually have a separate resistor going on like 3.3 volt power. Can you hear okay? Good? Or a question?
I had a question.
I'm sorry?
I had a question real quick.
Okay.
It's configurable. Is it configurable from a general standpoint, or will you specify it as an input and output because of that move?
You should be able to configure that. I just looked at just basically the actual I/O block. Depending on how in the Python code, I believe that the I/O library, that GPIO library lets you do that. So once again, really those I/O pins really aren't designed to drive substantial loads directly. An LED, probably okay, something like that, but anything more, not really designed for that. There's a couple of really good links here that I've got that talk where I got that cell structure from. You're welcome to look at those. So let's talk a little bit about how not to blow up a Raspberry Pi. Raspberry Pi and many other things are very susceptible to damage by static electricity. If you invest in a ESD mat and a wrist strap, that's a really good investment. You can go find on Amazon, eBay. They're weakly conductive, like rubber. It's like rubber with a weakly conductive substance in it that drains off static charge, so you don't blow things up. That's particularly important in the wintertime here when it gets really dry out. I mean, just moving around a little bit, you can build up several thousand volts in your body. You need to blow up a 3.3 volt logic pin, probably over 5 would do the trick. So, it's a really good idea. If your application can tolerate it, if you can put a resistor in series with your I/O pin, it buys you a great deal of safety for not much effort. If you just want to look and see what a pin is doing, it's fine for that. It can limit the amount of current. So if you short that pin out to ground, it won't that, we just use Ohm's law. So for example, R is equal to the voltage divided by the current. So if you want to limit the current to 10 milliamps, you would use 330 ohm resistor for 3.3 volts. Some terribles use 1 and 10K. That can work pretty well. Another way to protect things is you can use something called a TDS diode or a transor. Those are actually a kind of a diode, it's kind of a Zener diode that's designed to absorb transients and spikes. One problem is that to get the low voltage ones, most of those are surface mounts. You might need to solder little wires to it. Another thing that you can do is you can use 2 Schottky diodes between ground and 3.3 volts, which I'll show you in the next slide. And the way that can work is if you have a series R there, and something comes back and tries to drive that pin, say to 5 volts, or try to pull it below ground, these diodes will start to conduct, because they'll start to turn on and let the current go up to 3.3 volt rail, or it'll pull up from ground. So you can do that. That's another way you can protect your Pi. Let's talk a little bit about outputs first. That's what we allow these to do. So, anybody here, who here knows what transistors? Anybody here comfortable with that, or how hard is it? You know what transistors are? Okay, transistors. Not a whole lot of hands. Okay, let's talk about the most basic kind of transistor there is. It's called a bipolar transistor. So, for purposes of using it quickly, it has 2 very simple rules. So, first rule is a very tiny current flowing between the base and the emitter causes a much bigger current to flow between the collector and the emitter. It has 3 pins: base, collector, and emitter. Modern transistors today, somewhere between 100 to 500 in terms of current gain. So really small currents can make much bigger things happen. Another rule for a bipolar transistor is it starts to turn on when the voltage between the base and the emitter exceeds about 0.7 volts. Transistors can be used to make bigger voltages, control bigger voltages or currents. You can turn these into switches. They come in 2 different flavors. They come in NPN and PNP flavors. So an NPN transistor, you drive current into the base and it comes out the emitter and it makes a much bigger current flow through. In a PNP transistor, you pull current out of the base and the current flows through the other way. So you can build what are called complementary outputs with those by doing that. So with that in mind, here we go. Let's talk about, I had to talk about transistors first and talk about how to drive a relay. So anybody here know what a relay is? Let's see a show of hands. Relays, anybody? Okay. So a relay is an electromechanical switch. It uses an electromagnet to actually operate a physical set of contacts. So it lets a small signal basically close another set of contacts. So they're really good for turning on big loads like motors. They're rugged, they're easy to use, you can buy them surplus, you can pull them out of old appliances. They're nice that way. They come with normally on and normally off contacts. You can get them with multiple poles, so multiple sets of contacts. One thing that's really nice about using a relay is you get electrical isolation. So if you wanted to say turn on 120 volt load like a light or motor, you've got no electrical connection between you and it with the Raspberry Pi. Unfortunately, the Raspberry Pi can't drive a relay directly. It can't go out with current like its pins to do that. So we need to help it by using a transistor to do that. I'm going to show you a circuit that you can use to do that. And there are some subtleties to do it. So here's a little schematic that shows a simple transistor driver circuit for a relay. So Q1. Transistors are normally called Q. I don't know why they chose Q. I don't know the answer to that, but transistors are normally called out by Q. It's a bipolar transistor which amplifies the very small output current from the Raspberry Pi and allows it to turn the relay on and off, coil on and off. So one thing you're going to see in the schematic is you're going to see D1, that's a diode, just a regular silicon diode. It's very subtle why that's there, but it's very, very important. Without it, your circuit will work exactly one time. And then you may blow up the transistor again with the Raspberry Pi. The reason for that is that in a relay, the coil that's inside there has a property called inductance. When you run current through an inductor, it really wants to keep going. The mechanical analogy for an inductor is a mass. If I take a brick and I throw it and it hits a wall, it really wants to keep going. So it pushes with enormous force to leave a divot in the wall. Electrically, that can also happen as well. You put a big It shunts that flyback voltage around the relay and keeps it under control so it doesn't blow things up. So let's talk there. The components you're going to see here, you see R1 and R2. Those are two resistors that are tied to the base Q1, which is a transistor. So the first one, R1, that's needed to limit the current in the base of Q1. And then R2 is optional, but it's a good idea. So if you left the circuit disconnected and it wasn't connected to anything, R2 basically is a weak pull down to ground to keep that transistor off if there's something connected to it. So your motor wouldn't just randomly turn on. That's why that's there. You can also add an LED, like what I've shown here. The LED and R3 are there to show when the relay is actually energized. So I'll go through how to design a circuit like that real quick. So I chose some parts that are readily available from a vendor called DigiKey. It's one of my favorite vendors. I picked a little relay made by Teak Activity. It's available for $1.35 brand new. It's got a 5-volt coil, which works well because the input power of a Raspberry Pi is 5 volts. The coil in that relay has about a 46 ohm resistance. That relay is a single position, single throw, normally open relay. What does that mean? Well, it means that it's basically, it only has one set of contacts, which is closed. It's a really simple relay. It's like a normal switch. And it only has one set of contacts. But it's rated for 10 amps, so that can power a pretty good sized load. So how much current will that relay coil need? Same thing we did before, let's use Ohm's law again. I is equal to V over R, so if you take 5 volts divided by 46 ohms, you get about 108 milliamps to drive that coil. That's way more than the Raspberry Pi can do. So what we do is we use a 2N2222 transistor to drive that coil. So that transistor is rated for 600 milliamps, so it's got plenty of margin. It has a minimum gain of 100 with a current of 150 milliamps. So we need to make sure that we drive the base of the transistor hard enough so we keep it fully turned on all the time. We want to make sure that we're flowing at least 1 milliamp into it. I chose 3. That's a good healthy margin to make sure that it's on. So once again, use Ohm's law again. And it turns out we need about 1,300 ohms. So use a 1K. 1K resistor is pretty common. Most people have those around. For the red LED, the size of the resistor for an LED is also really simple. So when you power an LED, it looks like a floating voltage source. So when you have an LED is turned on, it has a voltage across it. Each color of LED actually has a specific voltage across it. So you just basically take 5 volts minus the forward voltage through the LED. That's the voltage that you have to control. And you just divide that by, say, 10 milliamps. You end up with about a 330 ohm resistor. So this is kind of more for you as a takeaway. I made a parts list for that circuit. So if you went to DigiKey, you could actually look up these parts to give you some actual real-world examples of things you can go get. Talk about another option. Another option that's really nice is called a solid-state relay. A lot of companies make these. Crydon is one of my favorites. They act like a relay, but there's no moving parts inside. It's all done with semiconductors and transistors inside. They still provide isolation, just like a real mechanical relay does. So it can provide safety. You can switch both AC and DC loads. They can switch very rapidly, but they're kind of expensive. They're between, say, $15 and $50 for normal ones. There's some really large ones too that are more expensive, but the ones you probably use are in that range. But even to drive a solid-state relay like that, they do require a certain number of milliamps of drive to them, so you still need an external transistor to drive out from the Raspberry Pi. So what if we could do something that was a lot cheaper and just take care of it all at once? So I got to talk about one more kind of device called a MOSFET. A MOSFET is another kind of a transistor. It's called a metal oxide shielded field effect transistor. That's what that acronym stands for. It has 3 terminals, the same as a bipolar transistor: the gate, the source, and the drain. They come in N-channel and P-channel type, which is kind of like the NPN and PNP. So in a MOSFET, no current flows through the gate. It effectively looks like an infinite impedance. But the presence of the voltage there, or the not presence of the voltage, They make excellent high current switches because they have modern MOSFETs, have resistance that's lower than mechanical contacts nowadays. They're in the range of a million ohms, a handful of million ohms. The way they work, for an N-channel device, if you drive the gate positive with respect to the source pin, it turns on. For a P-channel device, if you pull the gate low, make the gate go negative with respect to the source, it'll turn it on. So when you use MOSFETs, one thing you have to be a little bit cognizant of is that each MOSFET that you use has a maximum gate source voltage. If you exceed that voltage, the gate will actually blow through the damage the fab. And they are somewhat ESD sensitive as well, so you have to be a little bit careful. Okay, so what can we do? How can we use that to actually make a switch? All right, so let's look at this circuit. Q1 is kind of the heart of the circuit. It's a P-channel MOSFET, and that's the device that's actually going to do the switching. So it's going to handle the high current through it. So D1, that's a Zener diode. The Zener diode is a special kind of a diode, and it acts like a normal diode when you bias it forward, but it will break down. You can buy them in different voltage ranges. So when you exceed, if you put a backwards voltage across the diode, at a certain point, it will break down and start to conduct. They're actually made to do that. So the reason that's there is that's there to protect the gate of the diode, the gate of the MOSFET from being blown. So Q2 is another NPN transistor, kind of like we saw before. And its purpose is when you turn Q2 on, what happens is current starts to flow through R2, and it starts to flow through R1, but that pulls the gate, which is the bottom terminal of this MOSFET Q1 low with respect to its source, which is the side that's going towards 12 volts. And that will turn it on, your load will turn on. So then R1, oops, did I have a typo? No, sorry, R1, when Q2 is in the off state, R1 allows a little bit of current to flow in there and charge up the gate of the MOSFET and turn it off. So, and just like before, the R3 and R4 are there to limit the current into the base of Q2, and R4 keeps it turned off when you don't want to use it. Okay, so here's another parts list. You can look at where these parts are from. You can find cheaper MOSFETs if you want. That's just a nice one. It's pretty common. Has a really low RDS. It can handle fairly high voltages. So let's do the same thing and add a little twist to it. So I'm going to introduce a new component called an opto-isolator. An opto-isolator is kind of a cool thing. So can anybody tell me what color when you look at like a transistor or you look at a chip, what color are they? Anybody? What color are chips normally? Is that just a fashion choice, or is there a reason for that? Well, it turns out there's a reason for that. You want to keep the light off of the silicon inside. And the reason is all transistors are photosensitive to some degree or another, and you can design them to be very photosensitive. So you can make a really cool device called an opto-isolator. You basically have an LED on one side and a special transistor over here on the other side, and the light shines on it. The transistor turns on, but there's no electrical connection between the two. So why is that so great? Well, suppose your Raspberry Pi is over here on where it says GPIO in and Raspberry Pi ground. If you're on that side and something bad happens on the high voltage side, there's no electrical connection between the two. You might blow up Q1, you might blow up you might blow up other stuff, but your Raspberry Pi will survive. This is a pretty ironclad way of providing safety to your Raspberry Pi. So, as an example, they're not even very expensive. U1, I looked up on DigiKey. You guys know what a dip package is? Everybody know what that kind of looks like? The old-fashioned parts that have the pins sticking out of them. It's a 4-pin dip package. I think it's about 41 cents a piece if you buy one. If you buy 10, they're even less. So you can keep some of those around. They're very useful. Okay, let's talk about inputs. So now we want to bring a signal into the Raspberry Pi. So something happens over here, and I want my Raspberry Pi to read that. All right, let's talk about push buttons first. A simple push button connected to a GPIO pin. You can use the built-in software definable pull down resistors on the switch, or you can use an external one. That's fine. One really good trick though is if you add something like a 0.1 mic ceramic cap that goes between the Raspberry Pi pin and ground, it will keep you from mechanical switches when they close. You don't get a nice, just clean picture like that. It really does something like this. And if you put a capacitor there, it'll get rid of all that hash. You won't have erroneous switch reads. It buys you, the other thing it buys you is, remember I talked about ESD damage to your GPIO pins or delicate, somebody throws a static spark into them? Well, a push button is a really good conduit for somebody to walk up in the wintertime, they've been shuffling around, they walk up, they touch it, spark shoots into the switch. Well, that can get into your Raspberry Pi. Having some capacitance there can actually cushion that because you have to charge up that capacitor before the voltage can get high enough to damage the part. It's not perfect, but you're getting kind of a lot of bang for the buck here. The other thing it's good for is that if you're in an environment where you're around motors and other noisy things, if the wires going into your switch pick up noise, that capacitor will tend to bypass that noise to ground, and you won't get erroneous switch reads that are caused by EMI. All right, let's talk about level shifting. So let's suppose that you've got like something coming from a car. Car uses 12 volts, right? That's pretty common in a car. I want to read that. Well, I can't run 12 volts into a Raspberry Pi pin because it'll blow it up. Well, we can do a really simple circuit to solve that. 2N2222 or 2N3904, real common, 3-leaded part transistor. They cost about 6 to 8 cents a piece if you buy a big bag of them. So you can blow up a lot of them, not worry. But basically, you use it as an inverter. So what happens here is the GPIO pin is tied to the collector of the transistor, and your input signal that's higher voltage comes in here, and it basically turns that transistor on, which pulls the pin low. So a high becomes a low, but it's a really simple circuit. So if you can deal with the fact that your pin goes low in software as opposed to going high, which is pretty trivial, it's no big deal. It's a really simple circuit. And you can design this to withstand fairly arbitrary range of voltages. So let's try. So let's play the same trick again. Same opto-isolator. You can basically make an isolated digital input just as easily. I played a little bit of a trick here, which I'll explain. But the idea here is you use that opto-isolator, that transistor on the other side of it now, to pull the Raspberry Pi pin low by shining, but inside the part, the light shines on it, it turns on the transistor and pulls the pin low. But in order to make a circuit that can handle a really wide range of input voltages, if you know your input voltage, if you know what it is, you can just use a simple resistor. But I'm trying to show you a way to make a really wide range input. So I made a very simple constant current sink. It flows the same current through it, whether it's got 3 volts on it or 30 volts on it. And the way it works, it's made out of it only takes 3 parts to do that. I used a 2N22 transistor, which is the same that we did before. There's a resistor in the emitter, which is R2, which is 150 ohms. There's a red LED, and there's a 10K resistor. So what happens here is, remember that forward voltage I talked about with the LED? How it has, say, 1.5 volts across it? Well, we're going to use that to make a voltage reference. Turns out an LED makes a very nice voltage reference. So a little bit of current comes through R3 through LED 1, and it generates about 1.5 volts. That holds the base of Q1 at about 1.5 volts. And then R2, basically, that sets the current through the circuit. So remember I talked before that the transistor turns on when the base voltage gets above about 0.7 volts. So if we hold that at 1.5 volts, the voltage that will be at the output of this transistor will be 1.5 volts minus 0.7 volts. So we can set, that gives you about 6 milliamps, I think is what I set this thing up for. So it's a really simple circuit. Let's talk a little bit about, very inexpensive to build too. Let's talk a little bit about some more basic. This is grounding, signal integrity, and electrical noise. All right, let's talk a little bit about grounding and power distribution. So if one thing that you can do that will do you a world of good is if you use a single point grounding scheme when you build things. Don't daisy chain grounds from one thing to the other. That you can get ground balance and you'll have things that happen that can cause a lot of trouble. It's best if you if you have like say a 5-volt power supply that's powering everything in your system, for example, bring everything back and tie it there. So everything ties back to the same spot. Don't do what's shown at the bottom and just daisy chain from one thing to the next. I won't say your system won't work, but it's just generally it's bad practice to do that. Okay, this is another real basic thing. If you have like a chip, you want to talk to something like an analog to digital converter chip with your Raspberry Pi, or you have some little sensor like an accelerometer or something like that that's tied to it with some wires. You really want to put a small capacitor across it. The reason for that is the wires that come from the Raspberry Pi to your circuit, to your chip, have inductance. And when that chip tries to say suddenly do something, like draw a slug with a little bit of current, the inductance of that wire will actually stop it, and it'll actually cause the power supply voltage to bounce around. So if you put a capacitor right across the chip, it'll basically give it a little tank of charge right there that it can draw from rapidly, and it won't have that issue. A lot of chips will not behave correctly if you don't do this. Let's talk a little bit more. So another trick. So does everybody know if you have a wire and current's running through a wire, you generate a magnetic field around it, right? Does everybody know that? Like, remember you're a little kid, you wind wire around a nail and you make an electromagnet? Well, it turns out that when you have wires that are carrying power in your system, they do exactly that. And if you have a bunch of wires that are going different places, they're bundled together, those magnetic fields will couple into wires that are adjacent to them, and they'll induce voltages in them that you don't want. So one thing you can do is you can twist the wires together. If you have current that's flowing this way down a wire, and then you have a second wire that's coming back, and those two wires are tied together, the magnetic fields cancel each other out, you don't get crosstalk and other things. And the complement of that is that the same thing, if you have like a sensor, you're bringing that sensor back into your Raspberry Pi, it also is much less sensitive picking it up because it induces equal and opposite voltages of the wire that just cancel out. It's a very effective strategy. So let's see. A really easy way to make twisted pair wire, all you do is take a coat hanger, chop a piece of wire off of it, make a little hook out of it, put two wires, anchor them in a vise, or have somebody hold it under with a pair of pliers, tie the other end of the hook, spin it, just kind of rub your hand up and down a little bit, you'll get a beautiful twisted pair of wire that you can make yourself very easily. This is another one. This is another subtlety. DC motors. The most common type of DC motor is a brushed DC motor. They actually have physical brushes that are rubbing and actually to connect the rotor inside the motor. Well, they make sparks, they arc when they're spinning. And that arcing can actually generate really substantial amounts of electrical noise. Enough so that it can cause, say, computers to reset, it can cause all kinds of weird problems to occur. Actually, I dealt with that last year, very much so. I found out somebody didn't bypass something, and I had a sonar system that was just going berserk every time a wing would move. So what to do? Well, our friend the capacitor is back again. So the best way to do it is if you put one capacitor across the two terminals on a DC motor, and then you take and you tie two more capacitors, one for each terminal, and you solder it to the case of the motor. That's about a 75% solution. That'll really quiet things down quite a bit. If you still have a little bit of trouble with it, you can actually take something called a ferrite core. It's a little piece of magnetic material. You basically just stick it on the two wires that are coming into the motor, and that'll help knock it down a little bit more. As an example, you can buy just a simple little ferrite bead that I found on DigiKey. They're like 19 cents a piece. They're very inexpensive. Plug here for one of my favorite books of all time. We just got a new edition of it. Just came out last year. We're waiting. Last day it has been updated about 20 years, and the new edition just came out. It's called The Art of Electronics. If I was on an island somewhere and the only book I could have with me was one, that's the book I would want. If you read that book, it is an extremely applied book on electronics. It's very pragmatic.
One of the things I really love about it is it shows bad circuits as well as good circuits. It tells you why they're bad circuits. So you can learn a heck of a lot from that book. So, that's my presentation, guys.